Dr. Tapre, the HOD of Electrical Engineering Department. Today we are going to discuss the subject Power System 2, the unit number 6, HVDC Transmission Line, lecture number 3. So we will continue the remaining topic of the previous lecture of unit number 2. Next point is the line compensation. The AC line requires shunt and series compensation in long distance transmission, mainly to overcome all the line charging and stability limits. Series capacitor and shunt inductor are used for this purpose. The increase in power transfer and the voltage control is possible through the static wire system. In AC cable transmission, it is necessary to provide the shunt compensation at regular intervals. The whole picture of the pack devices family is shown here. It is the simple transmission line, HVDC transmission line. So in that HVDC transmission line, here we use this state form or state form, and here the power P at this coupling capacitor is Vs VR by X sign of that. Okay. The problems of the AC interconnected is when two power systems are connected through AC type synchronous interconnections, the automatic generation control of both systems has to be coordinated using the line power and frequency signal. Even with the coordinated control of the interconnected system, the operation of the AC type can be problematic due to first, the presence of large power oscillation, which can lead to frequent tripping. Second, increase in the fault level. Third, transmission of the disturbance from one system to the other. The controllability of the power flow in the DC line eliminates all the above problems. In addition, for asynchronous DC ties, there is no need to coordinate control. It is obvious that two systems which have different nominal frequencies cannot be interconnected directly with the DC ties and required to use the DC lead. Next point is the ground impedance. In AC transmission, the existing of the ground zero sequence current cannot be permitted in steady state due to high magnitude of the ground impedance, which will not only affect the efficient power transfer but also result in the telephonic interference. But ground impedance negligible for the DC current, and DC link can operate one conductor with ground return in the case of monopolar operation. The ground return is objectionable only when buried metallic structures such as pipes are present and are subject to corrosion with the DC current flow. Next point is the reliability. The reliability of the DC transmission is quite good and comparable to that AC system. An acoustic record of the existing HVDC line in the world is available from which the reliability statistics cannot be calculated. It must be remembered that the performance of the thyristor valve is much more reliable than the mercury arc valves, and the further development in devices, control, protection is likely to improve the reliability level. There are two measures of overall system reliability. First is the energy availability, and second is the transient reliability. In energy availability, this is defined by the energy availability is equal to the 100 multiplied by 1 minus equivalent outage time divided by the total time. It is in percentage. Equivalent outage time is the product of all actual outage time and the fraction of the system capacity lost due to the outage. In transient reliability is equal to the 100 into number of times HVDC performed as designed divided by the number of recorded AC fault. This is the factor specifying the performance of HVDC system during the recorded fault on the associated AC system. Recordable AC system faults are those faults which cause one or more AC bus phase voltages and drop below 90% of the voltage to the. Next is the transient stability. It is assumed that the short circuit level after the fault is not below the minimum specified for the satisfactory converter operation. Both energy availability and the transient reliability of the existing DC system with thyristor wall is 95% or more. So HVDC outage statistic it is given by this table. The equipment name of equipment next is the MTTF, yes, MTTR in out. So it is given by this chart. MTTF means the mean time to failure and MTTR is the mean time to repair. So by observing this chart or table, we see that the average failure rate of the thyristor in a wall is less than 0.6% per operating year. The maintenance of the thyristor wall is also much simpler than the earlier mercury arc wall. So thank you very much for attending this lecture.